Hello everyone, it's my pleasure to present you a talk focused on topic interpretability in topic modeling, which was made in collaboration with Sergei Koltsov from High School of Economics and my student Andrei Mavrin. So, since I have a lot of time, I will spend first part in giving more details of what is topic modeling, despite I believe that most of you already know this concept and are familiar with algorithms. I still explain some details. So, general idea of topic modeling is to have a collection of documents as an input and then find how the words are distributed among the documents and how the topics are distributed among the documents. So, this is widely used task in many practical applications, such as classification and ranking of documents in collection, topical search for documents, profile learning in social networks, because topics can be used not only for words, but for more general concepts. Also, news analysis and explanatory research of papers. So, with more notation, we consider that a document consists of words, but we skip the order, so we say that the document is a bag of words. Then we suggest that a collection of documents has a limited number of topics, and we assume that all words are generated only by topics, and each document is described by several topics. So, intuition for this is presented in the picture with a very famous figure. So we suggest that a document contains several topics, and the probability of observing each word in the document depends only how probable is that this topic is presented in this document, and how probable that this topic will spawn as this word. So there are plenty of techniques which were created for building topic models. I would name the last three. So probabilistic latent semantic analysis and latent declare allocation are the most well known. And also the last and the best is additive regularization of topic models, which was suggested by Konstantin Vorontsov, and it can be understood as a generalization of previous two. So, to put more formalism, first, let's say what we're going to do. We want to have estimation for probability of observing words, W, given document, D. We decompose it to a matrix product, phi and theta, where phi is matrix representing probability of observing each word given topic, and theta is the matrix of observing each topic given document. So after this, we can decompose our problem to finding such matrix decomposition, and we do this applying maximum likelihood principle. So we just need to find parameterization, which gives us maximum probability of observing this document collection with found parameters. Idea of additive regularization for topic modeling is quite nice because it helps to express all requirements for topics in mathematical formulas. So generally speaking, there are many parameters and many restrictions which can be expressed in natural language, which are requirements for topics. For instance, we can say that we want this matrix to be sparse enough, or we want to have topics quite dissimilar with each other, and many other. All they can be expressed in mathematical formulas and added as a regularization for topic modeling. So instead of only optimizing likelihood of observing a phi and theta, we also add a linear sum of regularizations, R, and then we solve this problem, maximizing likelihood and regularization for both parameters. Nicely, it can be still solved with expectation optimization algorithm, which is applied for previous models quite smoothly. The only problem is that these regularizers should be smooth. They should have derivative, but typically it's not a problem. So this is a general framework suggested by Konstantin Vorontsov, which is widely used these days for topic modeling. Okay. In general, topics are something quite abstract. We really do not say that topics should be topics. It's just a general concept, but intuitively we want topics which are built by models to be real topics. So we can work with them and we can interpret them. So one of general requirements, especially for people who are trying to apply topic models, is interpretability of topics. How can we express interpretability? Only with human assessment. So in 2009, word intrusion approach was suggested. It works in the following way. We take 5 the most probable words from topic and also add additional word into there, and then show these 6 words to assessor and ask assessor which of these words should be deleted. So if assessor is right, then topic is somehow interpretable. However, the main problem of assessing topic interpretability in this way is that, unfortunately, this is very time-consuming, and we need to ask people to assess topics manually. So there is an example of what we call interpretable topic. So words in the left column, I believe you can somehow connect them together. If we see a topic which has most probable words like milk, eggs, add, received, sugar, we may conclude that it's something related to food cooking. Right part is sonar, vocabulary, existence, Gucci, measure. I have no guesses how can they be connected, but maybe you have. If you have, please tell me. In general, we consider right results as something uninterpretable. So what we're trying to solve in this paper, we're trying to build an algorithm which can automatically build interpretable topic models. So when we first to do this, and there are plenty of works related to building something interpretable, all of them, most of them, are related to the most probable words. So maybe the first one was point-wise mutual information, which is known as UCI. The idea is to estimate how well associated each word in the list of most probable words. Probability of observing words is estimated using some external corpus, because typically there are not so much words in document collections we are working with to estimate probabilities. Also, there is improved version for such measure called normalized pointwise mutual information, where we just add logarithms for each of parts of division. Another second approach is UMass, which was suggested in 2011. The idea is quite similar to the previous one. However, we build non-asymmetric measure, and we also do not use external corpus to estimate probabilities. Instead, we use frequencies of words in documents. Another idea is not to estimate probabilities, but estimate similarities of words using word embeddings, which became quite popular. So in 2013, the idea was expressed in such nice formulas. We simply estimate how similar are top words in topic using some word embeddings which we learned on some external corpus. Also, topic interpretability was one of the main questions when the approach was suggested. So there are some requirements we can add. For instance, topic should contain only few words with non-negative probability. So we don't want topics with many words with small probabilities, but we want topics which has just some, like hundreds of words with positive probability and all other words with zero probability. Also, we want documents containing only few topics. We want topics not containing common words, because they should be quite specific. And also, they should be quite distinguishable, so words and topics should be dissimilar. And distributions of words also should be dissimilar. So, all this can be expressed in regularization format. So I simply do not add it because it will waste slides. So, also that how we can compare words. One of approach, which is super old, is to compare words using probability learned on the document. However, it's very hard to learn joint probabilities of pairs of words using documents, so it's not generally applicable. Another approach is to use word vectors. So, Sergei Nikolenko's paper is using embeddings to compare words. So, what we're trying to do? We're trying to build a regularization which can be expressed as a interpretability measure. So how we can express this measure? There is approach by Roeder and Both in 2015. They say that we can split this measure in 4 components. So we use these 4 components. Using them, we describe a configuration space from which we'll be choosing measure. Then we turn this measure as a regularizer, and thus we create an interpretable model. So, first of all, what are these components? We're still talking about most probable words for each topic. First, we should choose a method how we split them into pairs. But maybe not pairs of elements, but also pairs of subsets. Then we should choose a method for estimating word probability, both single word probability and joint probability of pair of words. Then we should choose a confirmation measure, which tells us how much one subset of words supports another subset of words. And after that, we should choose an aggregation function. So, general scheme is the following. We have a topic, which is the most probable words. We somehow split them, estimate probability for what we have split it, then evaluate confirmation measure for each split, and then somehow aggregate. Thus, we have a measure of how interpretable a topic is. So what are the elements of our configuration space? Let's talk about splitting methods. We can choose the simplest one, just all pairs of words, one by one. We can choose the order which is given by the probability of words. So, word with the more probable word, or word with a less probable word. We can choose 1 versus all. We can choose 1 versus some subset, and we can choose some subset and another non-intersecting subset. Unfortunately, methods with subset were not so good, so I'm not going to put details how we play with subsets. Okay, for probability estimation methods, the one Boolean document method is commonly used in UMass. So we simply count the number of documents in which word occur and divide it by the number of documents in the collection. Also, we can use a sliding window of different size on some external corpus. For this external corpus, we use articles from the Russian Wikipedia. We have 1.5 preprocessed articles. So both of these methods allows us to estimate probability of word and joint probability of word pair. For confirmation measure, we use we have implemented quite a lot. So they quite different. They show how much two sets relates to each other. For aggregation, we use quite arithmetic mean, mediana, geometric mean, and harmonic mean. So this can simply be implemented as a regularizar for RTM. So say that C is confirmation measure, S is a splitting method. So we just say that we want to maximize regularizar for a matrix Phi, and this should be written this way. I hope that some people find themselves saying that, this looks like coherence, and yes, this is a generalization of coherence measure. So, we have implemented everything I have described as regularizers, and now our idea is to choose the best regularizer. How to choose this? We use data sets. So first of all, we choose some methods for building topics. Basic one. We build topics, 1,200, using a collection of posts from Live Journal. They were in Russian. So we had posts and we had topics related to these posts. Then we asked assessors to estimate how well interpretable are resulting topics. So they had answered two questions. The first one, do you understand why these words turn out to be together in this topic? So how well related they are. The second one is, do you understand what kind of event or phenomenon of life can be discussed in the text on this topic? So these two questions came from sociologists, because we also do not want only to understand how closely words are, but what is the subject to which they correspond to. So each assessor should evaluate each topic model from 0 to 2, and then we evaluated the mean of these estimations. So now we have labeled data set, and we want to find an element of our configuration space, which would be the best to predict these assessor labels. We use Spearman rank relation coefficient between scores and between the scores of the model we have learned and assessor's marks. So the best regularizer was this one. So each pair, sliding window of size 200, difference, and arithmetic mean as aggregation measure. So this regularizer outperformed, and the difference is quite big, all the models we have compared to. All these models were also trying to predict this, say how interpretable topics are, and we are much better than everything we have compared to. Okay, so we have chosen a regularizer. Now let's try to understand how well it works. So we do the very same thing, but with another data. We have chosen 3 corpora, papers presented in conference in intellectual data processing, articles published in newspaper Izvestia, and text from Open Corpora. And we asked 3 assessors to mark results and topics. We compared 2 models. First, we used topic model from ARTM, which uses all the ideas I have presented to you about how interpretable topics should be. So there is regularizer for topic verification, blurring of background topics, and decorrelation of subject topics. The second model we compare with is our model. So we used all these regularizers and added our own I have presented previously. And we use perplexity for maximization. So let's see what we have. So on all this corpora, our model with new regulator is outperforming initial RTM without regulator. So this is statistically significant result. And let's look on how perplexity and sparsity of two matrices was changing. And generally, I'll talk about perplexity a bit more later. Let's first look on sparsity of two matrices. So we see, red one is the model with regulator, and blue one is original model. So we see that we decrease sparsity of theta, however, we increase sparsity of phi, but not so much. Unfortunately, we cannot say that we decrease in sparsity of theta. We expected that we'll have lots of elements with zero values. We really had, but not so much as we expected. But still, it's a good improvement. As for perplexity, we can see that we have lower perplexity than the original model. So it may look bad. However, in one of the first papers, it was shown that when the value of perplexity is high enough, then perplexity and human interpretability assessments are directly correlated. So when we want to increase interpretability, the perplexity will fail. This obviously corresponds to what I have presented. So, to sum up what I have talked, we have presented a new regularizer, which we have chosen from a configuration set of interpretability measures. This regularizer helped us to improve interpretability of resulting topics without worsening quality of topics. Yeah, and it was simple enough. In fact, all strange measures we added to the configuration space were not so important because, just let me show once again. It was quite simple. So, one with one, no subspaces, no subsets were required, arithmetic mean, nothing complex, sliding window, okay, and difference measure, which is one of the most simplest. So, my talk is over now. Thank you very much, and I'm happy to answer questions.
Did you use normalized tokens?
Yeah, sure.
Have you tried to teach your model with n-grams? Because when you try to use the covariance with n-grams, it's usually already not covariance. Or it was just unigrams?
Yeah, it was just unigrams in both terms. So, I'm guessing you are suggesting to use n-grams for evaluating probability of words? Yeah. So the main problem is that we still don't have enough data to evaluate it for unigrams because we built joint probabilities for everything. And it's really hard to build joint probability for two words, so this is why it's hard to build joint probability for anything with n greater than 1.
And is it right that you just use those metrics like sparsity and perplexity?
Yeah, sure. We use them to evaluate quality of resulting model. So because interpretability is something good, but there are just well-known measures of quality. Sorry?
Consistent? Other metrics, because all of these metrics very naive.
Yeah, quite, but they're just super general.
Okay. Thanks.
Any other questions?
Thank you for the talk. Question is maybe general about measuring topic quality. In your approach and in MTMI, in GMS approach, they all rely on assumption, not assumption, like you measure topics by top boards related to this topic. But actually, topic modeling is about making matrices topic board and document topic. So do you maybe try or know about some project that make another assumption, like when you present topic based on most relevant documents to this topic? Like you can have a set of some documents specified to labels, maybe multi-label specification, and then you just try to make a topic model for these documents, and based on your specification results, trying to relate like for blocks like documents.
So, yeah, we haven't tried, and we haven't seen anything related to thing you're suggesting, and I believe this may be because it's really hard to evaluate how well documents are described by topics. Because when you ask assessor to evaluate 10 words, okay, it's accessible. So we can ask them to do this 1,200 times. But when we would ask to do something the same for documents, so the person should at least not read, but to scan entire document, and it is super much to ask for assessor. So I think there is no such approach just because it's very hard to evaluate them using assessoring.
Other questions? Yes. How do you select the best size of the window, the number of windows? 200, what it means? Why not 300?
Yeah, we just simply had 50, 100, 210. So this was original size of window. In fact, we didn't play much with size of window because it doesn't change much. So there was difference between 10 and 200. It was quite big, but there was not so much difference in 50, 100, and 200 for what we have observed for the West model.
Thanks.
Do you have time for one more question? No? I have a question about assessors.
Yep.
Actually, it's kind of two questions. First of all, could you please tell us a bit more about assessors themselves? Because usually you should choose assessors really carefully so the understanding of the problem is not biased to something. And another question is, do you think that only 3 assessors need?
That's a good question. So we have 2 groups of assessors. The first group was labeling datasets from LiveJournal. That was a group. So I actually do not know them because they were from Higher School of Economics, and the datasets with which we were working. So on, this dataset, it was already labeled when we started to work on this project. As for these 3 assessors, they were students from IT and law. They were asked to assessor to label the data. I don't really think that in this case it's something you need special skills too, because it's a general understanding of text. So if you know language, you can make some conclusions about if words are related or not. Also, so here we used something very common and something not so common, intellectual data processing. So this is a conference on machine learning and artificial intelligence. And yeah, students had already know something about machine learning, so we actually didn't see a big difference between so these documents and, for instance, Corpora. Yep. About the number of assessors, yeah, for sure, the more we have, the better. Unfortunately, it requires a lot of time for assessors to do this. We didn't spend money for assessoring. We just asked students, as well as High School of Economics, ask students to label the data. So yeah, personally speaking, I really believe that if it would be 100% results, maybe would be different. But yeah, but unfortunately that's what we have. And in general, when we're talking about human assessment in this topic, in most of the papers we have 2 or 3 persons to assess data.
So that's it.